Good morning, everyone. My name is Anish Moharsan, and I am part of Group 40 with my teammates Zifan Zhang and Meghna Reddy. Today, we are presenting about 24-hour digital health assistance network design proposal, which focuses on revolutionizing patient-centered healthcare. The 24-hour DHA program aims to transform healthcare by emphasizing patient-centered care. Our programs connects three general practitioner offices in Minto, Cornell Park, and Liverpool to enhance healthcare services in these regions. Now, one of the key features of our program includes virtual surgeries, telemedicine consultations, and secure access to patient medical records. Accessibility is another important aspect of this program. With our digital health system, patients can receive care regardless of their time or location. Our ultimate goal is to establish a secure, scalable digital system that operates all the time, which allows healthcare providers to deliver timely and efficient services. Mm. Now, let's look at the main objectives of this program. Our system ensures 24 hours a day and 7 days a week access to critical services like telemedicine and remote surgeries, guaranteeing patients receive care all the times. We aim for HD video with minimal delays, ensuring smooth and uninterrupted connections. Mm, we secure patient information with encrypted backups stored on site for added privacy protection. We've also designed the program with scalability, and we back up patients' information in every 5 minutes. Lastly, our program includes interactive robots for remote surgeries that requires low latency, fast network connections. Mm, Now let's look into the initial network requirements necessary to support the 24-hour DHA program. First, we'll need a broadband network. The network must be high speed and low latency, using both Ethernet and fiber optic connections. Mm, to ensure security, we will implement firewall VPNs and multi-factor authentication to safeguard access. Also, all data will be protected using AES 256 encryption. Effective bandwidth management is also important. We employ quality of service protocols to prioritize critical services such as telemedicine and surgeries. This will help prevent any interruptions or delays in service. Mm, for data storage, we'll use a combination of local and cloud-based storage solutions, both of which we will be encrypted for added security. Also, regular backups will be taken in every 5 minutes. Our mobile medical unit will require constant internet access to ensure real-time updates for medical records and video calls. This will allow uninterrupted connectivity even during the emergencies. Um, let's discuss the flow analysis of our system. For telemedicine and video conferencing, prioritize bandwidth and minimal latency are essential. Using quality services, we will prioritize video calls to prevent disruptions and ensure smooth consultations. Uh, in remote surgery, minimizing latency is critical for seamless data flow. Bandwidth will be prioritized and redundant pathways will be ensured uninterrupted operations. For backup and storage, backups will occur every 5 minutes during the low traffic periods to avoid interference with critical services. While personal internet access for staffs will be allotted, it will have low priority than healthcare services.
5G internet is connected to switches to provide external connectivity to the internal network. It's actually communication with remote services, such as remote operating systems or remote data access. This enables high bandwidth and low latency applications, such as remote surgery or high definition video conferencing. By connecting to a switch, the robot controller can receive and execute commands from a remote doctor or operator, especially for scenarios such as surgical robots. Low latency and high reliability of robot operation are ensured. This is the core computing and storage device of the entire network, and all data processing and storage are centralized on this server. The master server is connected to all switches, providing control and management of the entire network equipment. Each room has its own LAN and uses a 48-port switch to connect devices in the room. Connecting to the main switch of the router provides root connectivity, ensuring that all internal network devices can access the internet and interact with external services. Backup cloud connects to the router and communicates with other network components through the master switch to ensure that the data of the master server is regularly backed up to the cloud, providing disaster recovery capabilities. This design increases data security and redundancy, ensuring that data can be recovered from the cloud even in the event of a hardware failure. The network design of these two offices is very similar to the network design of the Liverpool office. Only some hardware equipment is reduced, but it still has very high performance and has good scalability, even if more employees will join. In the 20-watt HR network design, we adopted a hybrid topology. DGT office has a greenhouse and for connecting servers, computers, printers, and HD video conferencing equipment. Offices are connected via a metropolitan area network to ensure efficient low latency data transfer. The design guarantees high-speed communication between the internal devices and ensures fast and secure data transfer between offices through fiber optics and VPN technology. To ensure that each type of network traffic is properly handled, we use peer-to-peer peer transport architecture. This architecture enables real-time data sharing for remote surgery and HD video conferencing. We also use cloud servers for disaster recovery to ensure data security and continuity. The network architecture is divided into a core layer, a distribution layer, and an access layer. The core layer uses high-performance routers and switches, handles large amounts of data transfer, and supports critical tasks such as remote surgery and video conferencing. The distribution layer manages the data flow within the LAN and is responsible for optimizing network resources and implementing security policies. The access layer is responsible for connecting end devices, such as computers, printers, and medical devices, and managing user authentication and permission control. Given the growing demand for future healthcare networks, we made scalability a core principle from the beginning of our design. Our design solutions not only meet existing network requirements, whether it's adding a new location or a new device, our network architecture can easily adapt without requiring extensive rebuilding or adjustment. Another key factor is that the system must be able to support an increasing number of devices and users. Currently, a number of people in each AP at the same time. When new features are introduced, such as the remote operation of mobile medical units or surgical robots, the network can be seamlessly integrated. Next comes redundant design. In a healthcare environment, data and service reliability are critical. In order to ensure the continuous stability of the system, we set up a multi-level redundancy mechanism. The first is data backup, which is backup every 5 minutes to ensure data integrity in case of emergencies. And all patient data is backed up with encryption, not only on local servers, but also on cloud servers that comply with Australian law, so that data can be quickly recovered in the event of a local failure. In addition, network redundancy is an important part of our design to prevent any single point of failure from causing service interruption. We have built-in alternate paths and redundant connections into the network architecture, especially in critical scenarios such as remote surgery, to ensure that the procedure is not interrupted by network issues. Each office is connected via fiber optic and VPN technology to ensure data transmission speed and security. In addition, we also set up an automatic switching mechanism. Once the primary path fails, the system will automatically switch to the alternate path to maintain business continuity. Finally, the backup strategy is also very important. Patient records and data are backed up every 5 minutes and stored locally and in the cloud in encrypted form. This not only complies with Australia's data storage laws, but also ensures that data is quickly recovered in the event of a hardware failure or other emergency, thereby reducing the impact on health services. Medical services are very time sensitive, especially in critical scenarios such as remote surgery and consultations. The system must ensure continuous operation for 24 hours without interruption. Even planned maintenance may affect patient treatment. So we need to ensure that service interruptions will not occur under any circumstances. One important aspect of remote medical care is video consultations, where doctors need to observe patients. In remote surgery, surgeons also need to control surgical robots via the network. So minimizing network delay is crucial to ensure accurate and safe surgery. Data security is also a critical aspect of our design. Therefore, we must prioritize how to securely transmit and store this data. To do this, we will employ a multi-layered security strategy, including robust encryption techniques and strict access controls, allowing only authorized personnel to access patients' data. As a U7, our data storage is not limited to local storage, but also utilizes cloud storage and backup mechanisms to ensure the integrity and reliability of the data. Additionally, the network must be scalable. Currently, the 24HR DIH project covers 3 general practitioners offices, but as the business grows, there may be more offices or mobile. Therefore, we have designed it to be scalable so that it can support expansion smoothly, regardless of how many nodes or functions are added in the future. Backup and redundancy design is important. Even if hardware failure or other unexpected situations occur, we must ensure that data can be safely recovered. Therefore, we have set up a regular backup system, encrypting patient data every 5 minutes and storing backups both locally and in the cloud.
Hi, this is Meghna. Now I'm going to discuss about the design topology. So we have designed a hybrid network topology for the 24-hour DHA that is connecting the Liverpool, Condell Park, and Minto. So this is the topology connecting the 3 nodes. Liverpool, it acts as a primary center. So it has got 5 offices and 5 offices where we have the host, we host the primary database and also video conferencing systems and even remote surgical robots for live surgeries. And Condell Park and Minto also are playing the key roles, with the Minto is having a primary backup server and the Minto and in the Condell Park having the primary backup server, and also the Mindo is providing the video conferencing and the remote access capabilities. So additionally, we have the mobile unit. So the mobile unit is represented through the laptop, and it gives the continuous telemedicine services via the 4G and the 5G emergency services. So that's about the topology network. And coming to the addressing, so to keep everything organized, we assign different IP addresses ranges from for each location. For the LAN Liverpool, it is LAN 0. For Condell Park, it's LAN 1. And Minto is LAN 3, and we also got the external IPs for the WAN connectivity, ensuring that these locations are securely connected to one another and to the external services. And for extra security, the data is also backed up to a cloud server in the Australia every 5 minutes to ensure the data integrity. Now coming to the key features of the network design, our network design focuses on the flexibility, reliability, and the security. The security features include the firewalls, VPNs, role-based access control, ensure access only for the authorized users, and the VPNs. We have made the firewall connections within the through the routers configurations, and VPNs are also made to promote the secure access of the patient data. And backup strategy, the primary database in the Liverpool with the backup in the Condell Park. The main primary database is in the Condell Park, while the secondary is located is by the cloud backup, which is updated every 5 minutes for the data integrity, and the data whichever is stored in the Liverpool. So next, coming to the design document, we have like based on the problem and the requirement, we have made some architectural decisions and the design decisions and architect and design decisions. So architectural decisions are going to be enacted in order to meet the design decisions, and the design decisions in turn will solve the problem statements and the requirements which are involved. So problem statements and solutions, we based our design on solving specific issues. For example, to ensure high quality video conferencing across all offices, we used a bandwidth LAN or WAN topology. To reduce network delays and improve performance, we implemented a DMZ and applied quality of service policies. For database security, firewalls and role-based access controls protect critical information. Additionally, we perform regular backups every 5 minutes. So this maintains the data integrity. We have set logging and monitoring tools. Now coming to the network performance metrics. So our performance metrics are like targeting 99.99% availability uptime, and latency that is minimized, especially for the critical applications like video conferencing, sufficient for the HD video and secure access to health records and scalability. Now coming to the life cycle considerations, the evolution of healthcare delivery models, particularly the 24-hour digital health assistant program, it necessitated 3 critical life cycle considerations like operational suitability, supportability, and also the confidence. So for assigning the operational suitabilities, the key features were like network design and operator capabilities. So these capabilities are made based on the critical questions and solving them. So like how will performance be monitored, what process exists for the issue management, how can patient request service improvements and such. And supportability, it assesses the system's operability, sustainability throughout its life cycle, like key factors like RMA, the reliability, maintainability, and availability. They guarantee the 99.3% reliability for critical services. So confidence, it measures the ability to deliver consistently without interruptions or degradations. For this, we consider error rate monitoring, so like regular assessments to identify the issues early, and fault tolerance designed to withstand data loss, ensuring uninterrupted essential communications. So patient understanding is also important, and even we have some repair services which we have included in case of faulty devices or anything. Thank you.